Okay, so we've been learning about reaction rates, and we learned about the integrated rate law. And we noticed that some of the problems will give a temperature, or they'll specify at a fixed temperature. And I mentioned that that's because temperature has an effect on the rate of the reaction. Most chemical reactions are very sensitive to temperature. As an example, a 10 degrees Celsius increase in temperature can double or even triple the rate of a typical biochemical reaction. So that's a huge change. So the rate constant is only constant if the temperature remains constant. You change the temperature, the rate constant is going to be different. You stay at that temperature, it's constant. Okay? So the temperature dependence of the reaction is contained in that rate constant. And we notice that rate constants generally increase with temperature. You heat something up, it usually goes faster. So this is the Arrhenius equation, and this is the same guy who has acids named after him, Arrhenius acids. Yeah. Thank you. I wonder who did that. Actually, I did that last night. Thank you.
Thank you.
Yeah, that's better, huh? So this is the Arrhenius equation. It's kind of a mess, right? So the rate constant is equal to a frequency factor times this exponential factor. So this E is not a variable, that's the anti-natural log. So E raised to the power of negative EA divided by RT. So this EA is the activation energy, R is the ideal gas constant, and T is the temperature in kelvins. As we learned in Chem 1A, the ideal gas constant has different values depending on the units that you use. And so here we need the units joules per mole Kelvin, so we're going to use the 8.314 for the gas constant. Okay, so in 1A we sometimes looked at energy diagrams, where we looked at the energy of the reactants compared to the energy of the products. And in this situation, the energy of the products are lower than the energy of the reactants. And since nature likes to go towards lower energy, this would be predicted to be a good reaction that would occur. It would be exothermic, right? But even if this is an exothermic reaction, energetically favorable, it may still require some energy. So now there's a hump in the middle, and this is known as the activation energy. This is a hump you have to get over before the reaction can proceed. And this reminds me of miniature golf. You know, you've got your little green over here, and then there's a hump, and then it goes down the hill, and the hole's down there where you're trying to go. And so if you just hit it enough to go over here, it's going to go partway up and roll back down. You have to hit it hard enough to get up and over the hill, right? If the hill wasn't there, you wouldn't have to hit it so hard. So this is the activation energy. It's a barrier, an energy barrier that has to be overcome. The frequency factor, A, in the Arrhenius equation, is the number of times the reactants approach the barrier per unit time. So in the miniature golf analogy, you could say, well, that's how many times per minute you hit the ball in an attempt to get it over. So the more frequently you hit it, the sooner it's going to go over, right? If you only hit it, once every hour, it's going to take a while. So that's the frequency factor. Any questions? So let's look at this reaction where we have methyl isonitrile rearranging to form acetonitrile. So this is kind of a weird reaction because the chemical formulas are really the same. It's just that a connection has changed. So the nitrogen and the carbon swap places when this happens. So we go from this molecule to that molecule. So the molecule has to go through an intermediate state that's higher in energy. And this is where that carbon-nitrogen kind of pulls out away from the rest of the molecule and starts to turn. And you can imagine, like, if, the atoms were hooked together with, stretchy elastic, you'd have to pull on it to get it to come out and start turning it. When you let it go, it's going to snap back in, right? So it's high energy, it's under stress when we do this. It's needed to weaken that carbon-nitrogen bond and allow that, this carbon-nitrogen bond, and to allow this to begin to rotate. So the energy needed to get to that form, that complex, is the oxidation energy, the activation energy. The higher the activation energy, the slower the reaction will happen. Because if you think about as it approaches, not all of the approaches are going to have enough energy to go over, but if that hump is lower, more of them will have enough energy to go over, and so the reaction will occur faster. Any questions about this yet? We're not done with it.
Wait, what did you say about the lower the hump again?
So if this hump is lower, if it takes less energy to get to this intermediate state, the reaction will proceed faster. So, with the miniature golf, I don't know about you guys, but when I hit a ball in miniature golf, I do not hit it the same every single time, right? I am not a professional golfer. I've been to Topgolf once in my life, and that's it. It was an experience. So you're hitting the ball, you're just putting, you're hitting the ball, and it goes up, partway up that little hump, and then it comes back down, and you're like, dang. So you try to hit it a little harder, and maybe it goes up further, and then, I don't know what happens, and then you hit it less hard. And finally you hit it hard enough, and it goes over. If that bump was lower, that second try might have gone over, might have had enough energy. And so the reaction would proceed faster, your game would proceed faster. Does that make sense? Yeah.
If it still goes over the bump, is it still counted as one of the approaches?
Yes.
Okay.
Yeah. So one of the approaches will ultimately send it over the edge. Yeah. Any other questions? So the frequency factor is how many approaches to the activation barrier occur per unit time. And so for this example, that NC group approaches the activation barrier each time it begins to rotate. So it starts to rotate and it didn't quite make it. It comes back down. And it tries again. And so that frequency factor represents the rate at which that NC group vibrates from side to side. You can think of this as like a dog wagging its tail, right? And so it starts to turn, didn't have enough energy, comes back. Well, how many times does it do that in a unit of time? Say a second. The more times it does that, the higher the frequency factor. Each time it begins to rotate, it has a chance of going over if it has enough energy. Any questions? I have some skeptical looks, like, Yeah.
So the frequency factor you said is how many approaches it takes to go over the...
Almost. It's not how many approaches it takes to get over, but it's how many approaches there are per unit time. Okay? So it might never go over, but it's going to try. How many times does it try in a second? That's the frequency factor. Any other questions? So then the exponential function in the Arrhenius, the exponential factor in the Arrhenius equation is the fraction of molecules that have enough energy to make it over the activation barrier. on a given approach. So this is going to be a number between 0 and 1. 1 would mean that all of the approaches are successful. 0 would mean that none of the approaches are successful. So if we had a frequency factor of 10 to the 9th per second, so molecules are approaching this barrier 10 to the 9th times per second, that's a big, big number, right? And if we had an exponential factor of 10 to the minus 7, which is 1 over 10 to the 7, this is saying that only 1 out of 10 to the 7th approaches is successful. So the frequency factor and the exponential factor get multiplied together to give us the rate constant. So that would give us a rate constant of 10 to the second per second, or 100 per second. So high frequency factor is going to make the rate go faster, and a high exponential factor is also going to make the rate go faster. And that, again, that exponential factor has to be between 0 and 1. Any questions? So the exponential factor is the part that depends on temperature. So this is the exponential factor, e raised to the negative EA over RT. This is the activation energy, and then we've got our temperature. So this factor depends on the activation energy, how tall that energy hump is, and on the temperature. When we have a low activation energy, when the hump is low, and we have a high temperature, so temperature, remember, is a measure of the average kinetic energy of the molecules, right? So at a higher temperature, the molecules on average are moving faster, right? When they're moving faster, they have more energy, they're more likely to go over the hump. So as you increase the temperature, then this factor is going to approach 1, where every approach is successful. And that's going to make your rate constant larger and your rate faster. Does that make sense?
What did you say was between 0 and 1?
The frequency factor.
Oh, the frequency factor.
No, I'm sorry. It's the exponential factor. That was a great question because I didn't even know the answer.
Okay.
The exponential factor, so that's between 0 and 1. So this is the exponential factor, and so this whole mess here is going to have a value between 0 and 1. And it represents the fraction of molecules that have enough energy to go over the barrier. If we have high activation energy and low temperature, now we've got a big hump to get over and the molecules are moving more slowly, then that factor can approach 0, where none of the approaches are successful. Does that make sense? So high activation energy makes it harder for the reaction to occur, and low temperature, with the molecules moving more slowly, makes it hard for the reaction to occur. Any questions? So if you have a sample of molecules, there's going to be a range of energy, right? The temperature is the average kinetic energy. But at a higher temperature, the average energy is going to be higher. At a lower temperature, the average energy is going to be lower. But what also happens is the distribution changes. So here is fraction of the molecules with this amount of energy. So at a low temperature, you'll see sort of a Gaussian curve here. And so, the average would be in here somewhere. Some of them have really high energies, some of them have really low energies, but the average is in here. When we increase the temperature, the average moves up, but the curve also spreads out. So if this is our activation energy, the area under the curve over here is the molecules that have enough energy to get over. And so we see that when we're raising the temperature, the area gets much larger, even though the average temperature still doesn't have enough energy to get over. Does that make sense? Because some of the molecules are really slow, some of them are really fast. and that distribution spreads out as you increase the temperature. When you decrease the temperature, it contracts, and they get closer together. So, summary of all that. Frequency factor, how many times the reactants approach the barrier per unit time. It's the frequency, how many times per second. The exponential factor is the fraction of approaches that are successful. You know, out of 100 approaches, 5 are successful. Well, then the factor is 0.05. If 50 are successful, then 50 out of 100 would be 0.5. So the exponential factor is going to be between 0 and 1. The exponential factor depends on temperature. It will increase with increasing temperature, but it will decrease with increasing activation energy. So this is the the exponential factor. So if this is a big number, we have E raised to a negative big number. That's going to make this whole factor smaller. If temperature is big, that's going to make this number smaller. E raised to a negative smaller number is larger. That may or may not make much sense to you. If you think of temperature being related to average kinetic energy, and you think about playing miniature golf. So increasing the temperature would be hitting the ball harder. The balls, on average, have more energy. They're more likely to go over. It's going to go faster, right? The activation energy is how tall is that hump. If the hump's really, really low, maybe all your balls go over, right? But if it's really tall, you might have a hard time getting any of them to go over. So the fraction that go over are going to be smaller. Questions? Yeah.
Will the negative sign on the energy ever be positive at any point, or?
This,
Yeah.
would it ever be positive? No. Because an activation energy, by definition, has to be a positive number. The ideal gas constant is a positive number, and temperature in kelvins is always a positive number. Yeah, good question. Okay, which statement best explains why reaction rates generally increase with increasing temperature? There's lots of words here, but these answers are fairly similar. The reaction rate increases with increasing temperature because, okay, they all say that. As temperature increases, a greater fraction of molecules have enough thermal energy to surmount the activation barrier. Is that true? Yeah, that's true. So this is looking good as the correct answer, but we got to check the others. Blah, 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 because as the temperature increases, the pre-exponential factor of the rate constant increases. So the pre-exponential factor was the number of approaches. Does that depend on the temperature? No, it doesn't. So this one's not right. And C, as the temperature increases, molecules decompose into their constituent atoms, which can then form new bonds to form the products. No. That sounds fancy, right? It's got a lot of words in it and sounds good if you don't think about it too much. But that's not what's happening. So this is the answer. Any questions? So the reaction rate generally increases with increasing temperature because the number of approaches that are successful is greater because they're coming with more energy. There's this barrier, energy barrier they have to get over. They have to have enough energy to get over that. If they have more energy, that's fine. They're just going to kind of go flying or whatever. but it has to have enough energy. So the temperature causes that factor to increase. So we can make Arrhenius plots of data. So the frequency factor A and the activation energy EA, how can we figure out what they are? Here we have the Arrhenius equation. What we can do is we can measure the rate constant at different temperatures. And we can rearrange this equation into a linear form. We're going to have, there's just going to be a lot of y equals mx plus b in this class. Y equals mx plus b. So y would be the natural log of the rate constant. So you do a bunch of experiments, you measure the rate constant, different temperatures, get a whole table of data. To graph it, you're going to take the rate constant that you measured and find the natural log of it. And that will be the y value. And the x value is going to be 1 over the temperature. So you measured the constant at different temperatures. So you take those temperatures and you invert them, 1 over the temperature. And that's how you get your points to graph. Then when you graph that, negative EA over R is going to be equal to your slope, and natural log of A is going to be equal to your y-intercept. So you graph a bunch of points, and then you can calculate EA from the slope, and you can calculate A from the intercept. Just the fine print here. The temperature dependence of A is a thing. A does change a bit with the temperature, but it's small. It's a small factor, and so we just usually ignore it. It's always convenient when you can ignore troubling things. Okay, so let's look at an example. The decomposition of ozone, O3 going to O2 plus O, is important in a lot of different atmospheric reactions. So they studied the kinetics of this reaction, and they measured the rate constant at a bunch of different temperatures. And these are temperatures in Kelvin. And so this is saying, find the value for the frequency factor and the activation energy for this reaction. So what we need to do is we need to make an Arrhenius plot. And that's using, so I had a student from the other section texting me last night because he was confused about, well, how can I make this graph if I don't know the equation? And so I'm like, that was a new question. The equation comes from the graph. So we don't know all the things in this equation when we make the graph. What we need to know is the value for x and a value for y. And then we can graph the points. So we have data, and we don't just graph rate constant versus temperature. You can make a graph, but it's not going to give us any useful information. So for y, we need the natural log of the rate constant. Well, here's the rate constant. So you're going to find the natural log of the rate constant. The calculator's in my box. And there's nothing mystical about this. You're just going to find the natural log of that number. So the natural log of 3.37 times 10 to the third is 8.123. So for each of these rate constants, you need to find the natural log of the rate constant. So you'll have another column of data. And if you didn't figure it out already, today in lab we're going to learn how we can make Excel do all of this for us. So we type in this once and it'll do all those calculations for us. It's a beautiful, beautiful thing. For X, we need to know what 1 over the temperature in kelvins is. So for 600, that's 1 divided by 600. So that's going to be 0.00167. So I'm doing some math on my data, and then I'm graphing those numbers that I get. Any questions about that? So here's the graph. So for all of those points, they found the natural log of K, and they found 1 over T, and then they graphed the points. Then you have Excel, do linear regression, and it's going to show you an equation for this line, okay? So from this, we can figure out what the frequency factor and activation energy are. If you need some help being able to see this form in a kind of messy equation like this, please ask me during lab. Because if you can't see it, then it's really hard to do these problems, and I can help you see it. It's not that hard. It's just, a little bit of practice. So again, this is the Y value. This is the X value. So then this guy, negative EA over R, corresponds to the slope. So the slope is equal to negative EA over R. And the natural log of A, the frequency factor, corresponds to the intercept. Bless you.
Thank you.
So from this equation, we know what the slope is. It's negative 1.12 times 10 to the 4th. So the slope is negative 1.12 times 10 to the negative 4. That is equal to negative EA.
It's 10 to the 4, not negative 4.
10 to the 4, thank you. Again, I wish I had done that on purpose, but didn't. So we have an equation here. And again, the algebra here is really simple, and yet a lot of students struggle with this, and they want to take this number and divide by R. That's not what's going on here. You can use the solver on your calculator here to find it if algebra is not your friend. So we know what R is. Let's write in the value of R. It's 8.314. I'm leaving the units off here. Maybe I shouldn't, but I am. So we need to solve for EA. So we've got a negative on both sides. If we multiply both sides by -1, the negative goes away, right? Well, that's a little bit extreme. To move the 8.314, we multiply both sides. So EA is going to equal 1.12 times 10 to the 4th times 8.314. Oops. Calculator saying 93116.8. What? Yes. Why are we multiplying and not dividing? So we need to rearrange this equation, right? So we want EA to stay here. We want the 8.314 to go to the other side.
Wait, where did you get that 8.314?
That's the value of R.
Oh, R.
Yeah. Those are great questions. Thank you for asking. So R is equal to 8.314 joules per mole Kelvin. We're not using the 0.008206 one here because the units are wrong. So what would the unit on the activation energy be? I mean, we could put the units in here and cancel them all out, but what should the unit of an energy be? Joules. So this has joules in it, so this is going to come out in joules. What would be a reasonable number of significant figures? 3. Yeah. So then we could call that 93100 joules. Just remember, anytime you're rounding to a place that's greater than 1, you have to be careful, because some people will round 93,116.8 to 931. And then if you're one of those people, I'd like to do some real estate transactions with you. And, oh yeah, this house is $455,972. Let's just round it to 425 and I'll buy it from you, right? That's not going to be okay. That's not okay. How do you avoid that? So here we're rounding to this place. Put the number in scientific notation as you round it. So in scientific notation, the decimal point has to go after the first non-zero digit. I'm kind of explaining some of these things because I know some of the people in this class haven't had Chem 1A for a while, and maybe they forgot. And maybe those that took it in the spring still forgot over the summer. So yeah, just throwing that in there. 9.31. I'm going to leave this a 1 because the next digit is less than 5. So I'm not going to round up. 9.31, those are the digits I want to keep. And then I'm going to times 10 to them. Now we have to count how many places did we move the decimal point. So I went 1, 2, 3, 4 places. So this is going to be a 4. Is it positive or negative? It's positive. Some people have trouble with that. I remember having trouble with that. This is how I remember it. Is this a big number or a small number? It's a big number, 93,000. How do I feel about big paychecks? Positive or negative?
Positive.
Positive, right? So big number, big paycheck, positive exponent. If it's a small number, like 0.0075, I'd feel negative about that. So I still count the decimal places, the exponent is negative. The books always talk about to the right and to the left, positive and negative, and that never made any sense to me. So I made up my own thing. So this many joules is the activation energy. Any questions? And then we have to find the frequency factor, A. I have no idea why they chose A for frequency factor. Sometimes it makes sense, many times it does not. So the y-intercept is equal to the natural log of A. Well, what's the y-intercept? It's 26.8. That is equal to the natural log of A. How do we get A by itself? You can't divide by natural log because natural log is a function, it's not a number. You have to undo the function. So here we had something divided and we did the opposite, we multiplied. So here we have natural log, we're going to do the opposite function, which is e to the x. So that means that e to the 26.8 is equal to A. And again, if that's something that gives you some trouble, use the number solver. Or, even better, try it, thinking it through like that, and then check it with the number solver and make sure you did it the right way. Okay? So I'm going to have e to the 26.8 equals. So that is, we decided 3 sig figs was pretty good, so I'm just gonna write down 3560. So that's the one we're gonna keep, times 10 to the 11th. So I'm gonna round that to 4.36 times 10 to the 11th. And what is the unit on that? It's a frequency per second.
Okay.
So on Monday, we had an example where the rate constant was in seconds and the time was in minutes. Second is the base unit of time in the metric system. So if we aren't sure what unit for the time, seconds would be a good thing to assume. Yeah, question?
Can you explain how you undo the natural law?
Yeah, so can I explain how I got from here to here? So what I did, I'll make this a different color. If I take e to the natural log of a, the natural log and the anti-natural log cancel each other out. Okay. Great question. Any other questions? Mm-hmm. How did I get this number?
Yeah.
Okay, so I took e to the 26.8. So your calculator should have an anti-log button. The base 10 log is 10 to the x. This is e to the x. E is this weird number. So I'm just doing on this, the 26x Pro, I'm pushing the e to the square button, and then I'm typing in the exponent, which is 26.8, and pressing enter. Yeah, good question. Anybody else?
I had a question.
Mhm.
So if we're finding the activation energy and the frequency factor,
Mhm.
what does that slope mean again? Like that equation? Is that like the rate constant?
No, the slope here isn't the rate constant. The slope is this thing
No,
right here.
but like that equation. What does that represent?
This equation, what does that represent? Okay, so that represents the computer finding the best straight line to go through those points. Process called linear regression.
Okay.
So if you looked at this red line that they drew and found a point on there, the y and the x would fit in this equation. The equation would be true. Okay, good question. Anybody else? Because in theory, all of you know how to graph stuff, but in practice, you've forgotten some things, right? Because you don't do it very often. So this is one of those things where you probably thought, why do we have to learn how to do this? Fast forward a few years and you're in Chem 1B and you're like, oh, I should have paid attention. It's okay. I'm happy to teach you math, right? Just all you have to do is ask. I just don't use the mathy words because I forgot them. So, we upside down it instead of taking the reciprocal. Oh, look, I got the answers right. Yay. Okay, for the decomposition of ozone, in that example, use the results of the Arrhenius analysis to predict the rate constant at 298 Kelvin. So we need a couple of numbers here. So that's one of the reasons that I'm writing all this out with the units here, because it's a pitfall. So common mistake, you're doing this problem on an exam and you forget to convert the kilojoules to joules. And so then your answer's gonna be wrong. So that's something just to watch out for. It's gonna happen in several other places throughout the semester. We're not doing it on purpose to trick you. Kilojoules would be used here because it's a big number. And the gas constant is in joules because it's not a big number. So how do we fix that? Well, you could just, convert, right? This is my shortcut way. I'm just gonna move the units over here. What does kilo represent? 1,000 times 10 to the 3. So what I'm gonna do is, instead of writing kilo, I'm gonna write what it means. K times 10 to the 3.
Did you write anything?
I did.
Yeah.
Oh, it's on top, my bad.
That's okay. Yeah. So here is the times 10 to the 3 instead of kilo.
Okay.
So those are equivalent. They're just different names for the same idea. And so that's a really easy way to convert. A lot of times when you're doing this, you need to get rid of a prefix. And so just put in its numerical meaning. Okay? So now my units are going to work out. So this is the exponent. Right? That's the same part. So it's e to that mess. So this could be an issue with you communicating with your calculator. Here we've got a number that's divided by two numbers that are multiplied. And so commonly students want to take this number, divide by this, times that. But the calculator doesn't understand that. That's going to get you this divided by this, that whole quantity times 298, and so your number is 298 squared too big. So watch out for that. You can put parentheses around here. Most of the time, you don't need parentheses when you talk to your calculator. If you're using the scientific notation button, there's no need to put parentheses around this. I do it when I write it out, just so that we can see that this is a separate number. But your calculator understands. So you can put parentheses here, or you could use that box over box button. So a lot of students might find it best to find the value of this first and write it down, and then finish the calculation. So let's just do that. Negative 93.1 times 10 to the third divided by the quantity 8.314 times 298. Close the parentheses. So that guy is negative 37.577. It's going to keep some extra digits. So were you able to get this number from that on your calculator? I forgot to put the calculators out. The calculators are always available. So it would be really great if one of the people that comes in earlier just gets them out for me, because I seem to be very good at forgetting them. Okay, so now we're going to take 4.36 times 10 to the 11th times e to the negative 37.577. you get that number?
Yeah.
You can also do the whole thing at once. But with the exponent and all the fractions, that can be a little confusing. So it's okay to write down this value. So that is a very small number. My rule of thumb for when should I write this in scientific notation is how many zeros are there at the beginning? There's 4. My eyes can only reliably see 3. I can see 3 zeros and be confident that it's 3 and I don't have to count them. Past that, they sometimes start to swim, and I have to get out my finger and count, and that makes me feel like a child. And so I don't like doing that, so I put it in scientific notation. Okay? If you have more than 3 zeros at the end of the number, then it would probably also be a good idea to use scientific notation instead. So we're going to record this in scientific notation. We're going to keep 3 sig figs, because that seems like a reasonable number. So the first non-zero digit is a 2. I put the decimal point, 0, and I'm going to round the 8 up to a 9, because of the next digit. 2.09 times 10 to the, and so I'm moving it 1, 2, 3, 4, 5 places. So I moved it 5 places. That's a small number. I have negative feelings about small paychecks, so this is a negative. Bless you.
Bless you.
Did I get the answer right? Yeah. Any questions? What about the units? This is kind of a problem because the units and the rate constant depend on the order of the reaction. We don't know what the order of the reaction is. I put units of per second on A in a previous slide, but most of the time they don't put a unit on it at all. So this has no units. This is e to the mess, and those units are canceling out anyway. So really, when we do this, k has no units. And, you know, on one level that bothers me, but why does k have any units at all? Only to make the equation of the rate law work out with units. So the units on k really are not meaningful. So there it is. Oh, they got 2.07. So they may have used unrounded numbers. Now, why are they getting units? I don't know where they're pulling those from. There's no place that says that this is a first order or a second order reaction. Yeah.
The table has the units for the.
Huh, thank you. There it is right there. Yeah, that's where they got the units. Thank you. Okay, so any questions? Oops. Did that. Yes.
I'm not getting my calculator and the answer.
Okay.
Negative 35.
Oops. Yep.
Why did it, because it says that we can use the results of the analysis from the previous one, but it kept the A value but not the EA. Why? Like, because the EA image is kilojoules instead of our one that was in this joules.
Well, they're using the activation energy in kilojoules. Wonder if that'll still paste. No. Because we got 93,100 and something, right? Joules, right? So you could just use that number in there. But I didn't write it down, I couldn't remember it all, and I had written down this value in kilojoules. Yeah. So typically what'll happen is the problem will tell you what the activation energy is in kilojoules. This is a multi-part problem where we determined it and then we use it. So we often don't have that number in joules to start with. That's a good question. Anybody else? Well, what if you don't have the luxury of being able to do an experiment and find all these points? We can use a 2-point form of the Arrhenius equation. How you go from the Arrhenius equation to the 2-point form is more than most of you want to know. I can show you later if you want to know. So this is the 2-point form. So now instead of the log of the rate constant, we have the log of the second rate constant over the first rate constant. That's equal to negative EA over R times 1 over the second temperature minus 1 over the first temperature. And we've lost the plus log of A. We can't find the frequency factor using the 2-point form, but we can find the activation energy. The frequency factor, honestly, is pretty useless. It's not very useful except in rare situations. So on an exam, you're a lot more likely to see the 2-point form. And so let's look at how to use that. And again, this equation is on your table of information that you will be given on exams so that you do not have to memorize it. The only reason I have it memorized is that I did this last semester. And so I happen to remember it. Consider the reaction between NO2 and CO. We're given the rate constant, 2.57 per molarity per second, and that's at 701 Kelvin. So these two go together, right? So T1 is 701 Kelvin, and K1 is 2.57. In here, the units and the rate constant are going to cancel out. So I'm going to be sloppy and not write them. That's not a 6. It looks like a 6. It's a problem. It's a 0. And at 895 Kelvin, so that's T2, the rate constant is 567. So the rate constant got bigger at a higher temperature. Does that make sense? That's what usually happens. Not always, but almost always. Find the activation energy, and they're specifying that they want the units kilojoules per mole. So we need to pair these up correctly. It really doesn't matter which one you call 1 and which one you call 2, as long as they're paired up correctly, okay? So we've got the K's, we've got the T's, we know what R is, we're solving for EA. So let's plug the numbers in. So the natural log of K2, 567, and that's divided by K1, and see those units cancel each other out.
Wouldn't it affect it if we did the other way around? If you call this one 2 and these 1, you're going to get the same answer. Oh, really?
Yeah, through the magic of math. We don't need to understand why. Negative EA, that's what I'm trying to find, divided by 8.314 joules per mole Kelvin, times the quantity, 1 over 895 Kelvin, minus 1 over 701 Kelvin. In Chem 1A, I almost always recommend rearranging the equation first, solve that equation for EA, and then put the numbers in. That's not a good idea here. This equation's a mess to rearrange for EA. It can be done, but most people don't want to. And so here, I think it's a lot safer to write these numbers in, and then you can find the value of that, right? And we can find the value of this and divide it by that. And so you might want to write down an intermediate step or two, and you're going to solve for EA. This is a place where you might want to use the solver. So let's try that out. It's not a very good marker. I'm going to pause it here because anybody watching the video is going to find the next part really boring because they can't see anything. So we plug that into the calculator. Calculator gave us 145096.78. What are the units on that? Joules per mole. So if we look in here, the gas constant was in joules. We've got a clue here that it's going to be joules per mole or kilojoules per mole. So we don't actually have to examine all the units, but we've got a joule in there, and so this is going to be in joules. These kelvins cancel each other out. And so units of joules per mole on EA would cancel these guys. So we're supposed to put it in kilojoules. So we need to move the decimal point 3 places. And so we're going to report that as 145 times 10 to the 3 kilojoules per mole. Is that the right answer? You've got it printed on your paper, don't you?
No, that's not.
It's not on there?
It says 1.5.
Oh, okay. So they're using 2 sig figs. But wait a minute. It's 1,500.
Because you know it's like 10 to the 3 kilojoules.
It's 10 to the
Like
10 to the second. Yeah. So that's 150. And I've got 1450. I'm off by a factor of 10. Duh, yes, thank you. Chemo brain is a real thing. Just, yeah. Okay. Yeah, so my brain was just like, ooh. So if we need to put this in correct scientific notation because it is not, because I did it wrong. Oh my goodness. Okay. We need to put it over here. 1, 2, 3, 4, 5. So, yeah, I tried to take a shortcut and it was a bad idea. So 1.45 times 10 to the 5th joules per mole. And then we need to convert to kilojoules. What they did is they rounded it to 2 significant figures instead of 3. I'm right, I just faked myself out. It does happen, doesn't it? And so I completely understand when it happens to you, right? Because it happens to me too. Okay, any questions? So use those results and the given rate constant at either of the 2 temperatures to predict the rate constant for this reaction at 525. So I'm going to use these 2 guys, 701. Oh, my brain's not going to be able to handle this. And then we're also going to need to use this guy. We're just going to use what the book said was the answer. Okay. Temperature, 701 Kelvin, not the rate. Rate constant at that temperature was 2.57, right? And then we need EA. It would be better to use the unrounded one, wouldn't it? And that's what I've written on the board, so I'm gonna write that one down. 1450.97, and that's joules per mole. Okay, we want to know the rate constant at a temperature of 525. So we're going to use that 2-point form of the equation. And plug things in. So the natural log, we're looking for K2 divided by K1 is going to be equal to negative 1.45097 joules per mole divided by 8.314 joules per mole Kelvin. One over T2. T2 is 525. T1 is 701. So, on this one, let's just do the math on the right side since there aren't any variables there. I've got negative 1,45097 divided by 8.314 times the quantity 1/525 minus 1/701. And I'm getting negative 8.34610. Anybody else get that number?
Yeah.
Yeah. So we see that the units are canceling out. Joules per mole cancels joules per mole, and these kelvins cancel the kelvins. This has units. I'll write them up here. So most people aren't going to have too much trouble getting to that point, right? I don't think there's any point in plugging this whole thing into your solver. That's a lot of stuff, right? We can solve this and write it down. Now some of you might want to use the solver. So you go ahead and use the solver. I think you got the hang of it by now. What if we don't use the solver? Well, we need to get rid of this logarithm. So I'm going to do e to the x of both sides, and these guys go poof. So now I've got K2 divided by 2.57 is equal to e to the number I just calculated. 0.000237319. And then to solve for K2, I'm going to multiply both sides by 2.57. Did you guys get this number? Cool. So then I'm putting that in scientific notation and rounding it to 3 sig figs as I go. And what would the units of that be? It's going to be the same as the units on the other rate constant. So they got 6.13. Am I going to worry about that? No. That's uncertainty in what we're assuming is the last significant digit. And, you know, if it was like 6.19, I might get a little concerned because that's getting close to the next digit. But 6.10 versus 6.13 is just a difference in which numbers you used in the calculation. So if you look at the rounded values that the book has and use those, you might come up with the answer that the book is giving. Any questions? I think we're close to the end of this section. We're not going to start the next section today. Reaction A and B have identical frequency factors, but reaction B has a higher activation energy than reaction A. Which reaction has a greater rate constant? So bigger rate constant, does that mean the reaction goes faster or slower? Faster. So we're looking for the one that's faster, right? And this one has a small activation energy, this one has a big activation energy. Playing miniature golf, this one has a big hump to get over, and this one has a little hump to get over. Which one's going to be faster? A. Now, Not gonna do it. It's not going to. We're gonna stop there.